proceed. Okay, welcome to the AstroAI lunch talk. Today it is my pleasure to introduce Yanke. Yanke is a final year grad student at Harvard Statistics, and he has been working with some of our colleagues here and myself on a project to do representation learning for X-ray sources. So that's what he's gonna be telling us about his Poisson Process AutoDecoder for X-ray sources with some applications on time domain astronomy. And the floor is yours, Yanke. Thank you so much for giving the talk.
Thank you, Rafael, for the introduction. I should say first that probably everyone here knows more astronomy than me. I'm just a statistics person, so apologize in advance if I make some mistakes. Yeah, but this project actually started last year from a discussion up to me, Ashley, and Rafael in an AstroStat group. But it's very related to machine learning. I guess that's why I'm giving a talk right now. The project is about a Poisson Process AutoDecoder for X-ray sources. I'm first going to talk about the motivation. So we're mainly interested in learning X-ray sources from the X-ray services. The X-ray service now produce massive amount of X-ray data where I made some simplification where I assume that the data just contains event files of photon arrivals. It's basically a collection of TI and EI, where TI represents the arrival time and EI represents the photon energy. So it's a series of photon arrival recordings. I made some visualizations just to give a clear idea. Here I ignore the energy marking and I just record the time and I make a histogram. I should say that this histogram is bent at an arbitrary bend, and in fact these points are just like time values. So we can see that there are different types of sources being displayed here. This is probably a flare where there's a sudden burst of photon intensity. Here's a dip where there's a decrease in photon intensity, possibly because another source is blocking the target source. And this one is periodic, there's a rise and falls in photon intensity. This one is, I put a question mark here because it's likely a homogeneous source where the underlying rate might be constant, although we see some variations in individual photon arrivals. So obviously these are very different type of X-ray sources, and because there are a lot of them, we just cannot differentiate them all by hand. So we want some automatic pipeline to learn these kind of sources. Some downstream tasks we have in mind is source type classification, where we can try to classify these different types of sources in terms of astronomical objects, and anomaly detection, where say we just want to discover all the dips. That's another target task. So there has been actually many previous work on automatic learning of these types of sources. There are both supervised and unsupervised learning tasks. By unsupervised, I mean that all the data we have are those event files. And by supervised, I mean there are also additional labels. For example, the true type of source as labels, and that provides additional supervision. So for both supervised and unsupervised, I use another type of classification for these words. One type of work, I call them manual feature selection, where basically researchers extract a set of features from those event files. I'm going to give an example of what kind of features are in there. But those type of features often requires domain knowledge, and it might also require time-consuming pipelines. So for example, these are the set of features that are used from previous work. we can see that some features include hardness ratios, which are just some kind of ratio between the photon flux from different energy bands, soft, medium, and hard bands. This one I actually don't understand, but from the description it says that you need to fit a physical model, and this is the parameter out of the best fit. And this is another parameter from the best fitting physical model that you need to perform. These three variables are from an algorithm called Gregory-Loreto, which is a statistics algorithm that I'm going to introduce very briefly pretty soon. But to sum up, like we see all these different kinds of features which are produced probably from different models, which either require domain knowledge and require time-consuming pipeline. So that's one set of work. Another set of work instead uses the power of machine learning. They fit deep learning models such as convolutional neural network or recurrent neural network to the data to extract features like in a more abstract way. However, all these works require the reconstructed light curve as the input data rather than the event files. Probably everyone knows light curve, but I'll just reiterate. So light curve basically means the real underlying rate. So for example, these are just bin event files, but probably if you fit underlying rate function, there are like some kind of smooth curves. And for this, it's probably a more flat curve. Because we assume that it's, I think, typical to assume that these photon arrivals follows a Poisson process. Then in another language, the light curve is just the Poisson rate function underlying these event files. So basically, all these kind of deep learning works needs a reconstructed light curve first before these light curves can be fed into these neural networks. Which means we need first a light curve reconstruction method. So for light curve reconstruction, we can obviously just bin those event files like I showed earlier. But you can probably see that, like if I return there, this is likely a homogeneous source. But if you just bin the event files, you see these ones and zeros, which are kind of the artifacts that might negatively impact the learning process.
So, Yanke, when you say that that's likely to be homogeneous, what you mean is that the deviations you see from like just having one count are completely consistent with just a Poisson process with a fixed rate of like one count or something like that?
Yeah. Like if, obviously I don't know the underlying light curve, but if the underlying light curve is just a homogeneous one, then it's not surprising to see an event file like this. Versus for the others, it's probably very likely not a constant light curve. But yeah, I put a question mark here because yeah, we don't really know whether it's a homogeneous one. So I'm going to continue about light curve reconstruction. So naive binning obviously creates these kind of artifacts because the Poisson arrivals are noisy. Then there's this more rigorous statistics-based method called Gregory-Loreto algorithm. It's a full Bayesian approach. I'm going to introduce like very roughly how it works. So I first consider all these stepwise light curves up to a certain frequency, meaning that it consider all the hypotheses containing a constant light curve, a two-step light curve, a three-step light curve, all the way to computational limit, which is usually 20-ish stepwise light curves. It gives a prior for all these hypotheses, and it computes the Poisson likelihood from all these hypotheses, which gives you a posterior likelihood. Then it superimposes all these proposals or hypotheses weighted by their posterior. To give an example of how G algorithm looks. This is one of the screenshots I took from the GL algorithm paper, where this dashed line is the simulated true light curve. And these are upper bounds and lower bounds from the reconstructed light curves of GL algorithm. So we can see it is piecewise linear because these hypotheses are actually piecewise linear. Because you need to compute the likelihood and posterior, which is pretty computationally expensive. That's why you can only do up to say 20 piecewise linear. So this is actually one of the drawbacks of GL algorithm, which is that its resolution could be limited due to computational complexity. Another drawback, which is not necessarily GL algorithm, but is the whole pipeline, is that if we use GL algorithm first to reconstruct the light curve, at the next step, we need to fed these light curves into the deep learning network to discover different kind of patterns. So these two algorithms are actually kind of disjoint, and it would be great if all these things can be learned end to end. So here are all the motivations in previous work. And in this work, I'm going to talk about a pipeline that can do these following things. First of all, it's fully unsupervised, meaning that we only need the raw event files to do the learning. It respects the Poisson nature, meaning that it can emit, or like it can filter out these noisy artifacts from the Poisson arrivals. It has infinite resolution, and in fact, if you see the reconstructed light curve later, it doesn't have these piecewise linear kinks. It is end-to-end, meaning that we learn a light curve reconstruction as well as a representation at the same time, where these representations are like very information rich and can be used for downstream tasks.
So, can you clarify? Can you clarify for the group what you mean by representation learning?
Yeah. So representation learning, it basically means you have very different type of modality of the data. The representation learning creates basically a set of vectors for each data point, so that you can use these vectors for downstream tasks. So our original data are like event files, which could be very noisy, and it contains different number of events. So it's very heterogeneous. A good representation learning method hopefully created one vector for each event file. And you can basically use these vectors for any task you want. For example, classification. You would just use a very simple classification method on these representations, and it gives you very good results. Yeah, this is probably a more popular term in the machine learning literature, but it's yeah, right now used everywhere. Great. So I'm going to introduce my method, our method. As a further simplification, I'm first going to ignore the energy marking, but I'm going to add them back later. If they're ignored now, we just have a series of time points recording the arrival time for the photons. So suppose we have a hypothesized light curve rate function R, then it is this formula is actually a very well-known formula from both statistics and probably astronomy, that the likelihood of observing this event file given this hypothesis light curve is given by this formula. This is just the Poisson likelihood formula that I take from the literature. Now, if I rephrase it in machine learning terms, in statistics, we want to maximize the likelihood, and in machine learning, we want to minimize some loss function. So I just use the negative log likelihood as a loss function to minimize. Just to remind you that this R is undetermined yet. It is like a hypothesis or something that we want to fit. However, in fact, if we only use the likelihood, then it's not enough, because let's consider this event file. We have previously showed this, and consider this very peculiar light curve where it only has positive values at those arrival times and has 0 values elsewhere. Then if you look back at the likelihood, it's going to give you basically a very large likelihood. But we all know that it is very, very unlikely in practice that these light curve can happen, because it has very large jumps, and it's just very probably impossible that it only has positive values at those arrival times. And in fact, true light curve, if we really think about it, it should be kind of smooth, meaning that it doesn't have huge jumps and very frequent jumps at those at very consecutive times. So there is a smoothness regularization that I'm adding here, just to make sure that the reconstructed light curve are relatively smooth. But obviously, we also have these type of events where there is probably actually a jump in the light curve. So we also want to make sure that the regularization doesn't filter out these kind of variations. So the loss function I'm using here is the total variation penalty. It is kind of equivalent to putting an L1 penalty on the derivative of the light curve. If you're familiar with statistics, L1 and L2 penalty are two type of very common regularization penalties. Compared to L2, L1 sometimes L1 usually encourages these kind of short but large jumps versus the L2 penalty. That's why I'm using the L1 penalty on the derivative, which is equivalent to total variation penalty on the light curve.
So you're saying you're gonna use your loss function that will be a Poisson loss function, but you're gonna add some sort of prior to this regularization to help avoid the overfitting of every single Poisson deviation from the main range. Is that right?
Yeah, exactly. Yeah, this is some kind of abstract prior that helps the shape of the reconstructed light curve. And the loss function is just a weighted combination of the likelihood and this PV penalty. A small technical details here. For the TV penalty, I need to sample a bunch of points, right? I'm here sampling two set of points. The first set of points is the Poisson arrival times. Another set of points is the, let's call it outside points. It's basically a uniform sampling of the points, which usually falls out of these arrival times. The reason I'm doing this is I want to provide enough coverage. So for these low count events, if I only focus on the arrival times, then we don't have enough variation for outside points. But for this very high count event, if I just sample the outside points, then that's probably not dense enough at this high count region. So,
That's very lovely, actually, especially, I mean, that's kind of the penalty that you actually define, because I think if you also have a set of emission laws, I mean, this should be generic, right? As soon as you have some discrete patterns, you can just use this one, right? I mean, my question may be a little bit more generalized. Do you have any other smoothing pattern or a smoothness regularization where you have a sharp, like events and nothing in between, or can it just capture all the things that you're just like looking for?
Yeah, this regularization usually encourages the thing you mentioned, where it's just a sharp burst and nothing elsewhere.
And if you have like, I mean, here, I don't know what is the duration of the time. Imagine that you have a very, very wide range of time, like a very wide range of events that they might be completely independent of each other, their appearance or disappearance, or you have a hyper geometrical models that is mainly multi-dimensional. Can it be just naturally used, or in the machine learning community, would that be any other better regularizers actually?
Yes, if you have some physics process behind it, and you know some, like in machine learning we call this inductive bias, basically means prior knowledge or like domain knowledge, then you can possibly define a better loss function or penalty. But that requires further supervision or domain knowledge. So that's definitely a potential future work direction, but here I'm assuming like the least amount, because I myself know very little astronomy knowledge, and in this pipeline I'm assuming like the least amount.
Great, okay.
Okay, I'll continue. Yeah, so I've just finished talking about the loss function for the reconstruction, right? But recall that we still need to fit this R, because this R is like hypothesis, and we want to find the best R that minimizes the loss function that I defined. So we need a parameterization of these light curves. The naive idea, we can probably use a parameterized basis function. As an example, the GL algorithm that I just talked about in previous work, they use the piecewise light curves. And we can define like say if it's a 20 piecewise light curve, we can just put 20 parameters at each time points and fit those parameters. We can also use other kind of basis functions, for example, like Fourier basis or wavelet basis, some other choices. It has either one or two of the limitations. If we use a piecewise linear, its resolution is limited. If we use some other basis, it requires some kind of domain knowledge. And it's also limited in resolution if we think about it in other domains, in other space. For example, we use Fourier, then its resolution is limited in the spectral domain. So what I'm using instead is actually becoming very popular in machine learning literature. It's called a neural representation. Basically, it means we represent the underlying signal with a neural network. In our case, the underlying signal is just a light curve. The good thing is that it has infinite resolution, because I can just input this neural network, input the t in it, and the neural network is just going to yield the rate function or light curve at that time t. And it's very flexible and powerful because a neural network can, in theory, fit any kind of shapes, and it's not limited or not constrained to this set of basis functions. So, and also because neural network can just be fit with gradient descent, we have defined the loss function. And now we just need to initialize a neural network, and we can just fit the weights of this neural network via gradient descent. Another small technical details here. Although a neural network, in theory, can fit any shape of function, it usually has some different capacity in practice. So what I'm using is a very generic neural network, which is a ResNet with ReLU activation. But ReLU activation, although it's very commonly used in neural networks, it is a piecewise linear activation. So it's not very powerful in learning high frequencies. For example, those very sharp flare that I just showed earlier. So what I'm doing instead is I'm going to increase the power of the neural network by doing a transformation of the T before I fit it into the neural network. By doing transformation, it basically means I'm taking the normalized T as well as a series of sine and cosine encodings of T. What this does, this positional encoding is actually invented in the transformer paper. I'm going to take a question now.
Sure, yes, I was wondering, what do you mean by infinite resolution? Because I imagine, like, if you feed something with two linear functions, you still have infinite resolution in terms of retrieving value, right?
Yeah.
But it's not infinite resolution.
Yeah.
And in this case, the resolution should depend on the size of your network, right?
Yeah, exactly.
Okay.
You're right. This resolution is not very well defined, but like it's usually, because a neural network, it usually contains millions or billions of weights. So, and it's like, the neural network is really complex and deep. So,
Okay, so
like
it's a
a
big model.
yeah, it's a big model.
Effectively infinite resolution.
Yeah, effective infinite resolution. Right. So, although I'm doing this sine cosine encodings of T before fitting into the network, notice that these doesn't necessarily constrain the shape of the reconstructed lacquer because all these things are still fit into the neural network, which can do some very complex things and produce other type of shapes. But it just turns out from the transformer paper as well as other neural representation paper that these positional encoding are very helpful. Without it, you need a much larger neural network to fit. But with it, the network is going to have a much easier time to fit different pairs.
So are you using the completeness of sine and cosine basis for doing this, like for choosing this positional encoding?
I'm only using up to some frequency. So the L I'm using here is 12, which is kind of arbitrary. But it usually doesn't need to be very large. Because otherwise it defeats the purpose of flexible fitting, I guess.
And in fact, I'm just asking a very simple question. The basis that you use, even if you don't go to infinite, that must be at least to some point representative, like a complete base, right? Like an orthogonal and complete base. Is that true, or?
I'm not sure what do you mean by complete.
Like mathematically, sine and cosine are complete.
Yeah, I know. Yeah, probably. Completeness is a very good property. You could potentially also use other complete bases, let's say piecewise linear bases, but I mean, because neural network is already piecewise linear, so I guess you need a different kind of complete basis. It's not that any complete basis will work.
And a very tiny question. So capital T in the denominator, doesn't it already provide a scale or like some kind of resolution to your analysis? Like, because that's like, you could have different lag times, so you could have play with the magnitude of capital T, like enlarging this or actually making this small. Would that affect the final result? I would imagine yes, but because you skip, right? So
Yeah.
if that's very large, you skip a lot of events in between. And if that's very small, you just keep them all, but you also add lots of noise. So there's a trade-off.
So the T I'm using, I'm not doing any random choice. T is just the lifetime of the event file. So we basically need to consider the event file to be of, like the lifetime need to be the same. Otherwise, if we compare like an 8-hour event file versus a 16-hour event file, it doesn't really make sense because we don't know what will happen for those 8 hours later, right? So I'm choosing all event files to be 8 hours, and this T is just 8 hours. The reason I'm normalizing it is because the neural network usually needs the input to be of standard scale to operate well. So if this t is 8 hours, then it doesn't learn very effectively. So I'm normalizing it so this t bar is between 0 and 1. And you know, all these sines and cosines are between -1 and 1. So they're the very same scale, very similar scale. Then the neural network can learn very well. Yeah, okay.
So for all the examples on which you train, the duration, total duration of the observation will be the same.
Yeah,
There might be different numbers of arrival photons, but the duration is the same, right?
Yeah, the lifetime is the same.
You don't really mean the lifetime, do you? Don't you mean the duration? Because otherwise it's a non-connected set.
I'll repeat the question. So probably I used the wrong word. By lifetime, I actually should use duration, where it's the time that I'm truncating the event file for like an apple-to-apple comparison.
Yeah, you ignore the dead spots that are all the way through it.
I don't really understand that spot.
Just in measurement, there is a lifetime. You know, an instrument is sensitive for a certain amount of time, then it's insensitive for a certain short amount of time, and then it resets. So that's just a detail, sort of.
I think what he means by lifetime is just the duration of the observation. Yeah.
That's a good point. I didn't know that instruments turn off for some period, but yeah, I'm assuming these data already took care of that. So yeah. Right. So the thing I've already talked about is already enough for fitting a light curve, because remember we already have a loss function defined, and now we have a way to represent the light curve with a neural network. Now we can fit the light curve. But remember that I already talked about earlier, one of the motivations for this work is that we want an end-to-end pipeline. Although we can reconstruct a light curve right now, we need some other method to learn the patterns of different light curves for efficient learning. So instead of designing another pipeline or use some CNN RNNs, I'm going to incorporate representation learning into our pipeline. So recall that like if some of you are still unfamiliar with representation learning, here's what representation learning is done most simply, in the simplest way in machine learning literature. It is first invented for images. So I'm first going to talk about that and see if that can be applied in our case. So in images learning, one of the very famous structures is called autoencoders. What it does is you feed an image as an input into this first neural network, where they call the encoder. It is kind of a bottleneck network because its output is of much lower dimension than the input. Say it's just an order of 10 or something. Then there's a second neural network called the decoder that maps this latent back to the original data format, which is an image. So if the output and input is trained via a reconstruction loss, so try to reconstruct the original image from this pipeline. Now, because we have this bottleneck layer, then the whole neural network is trying to learn a dense and abstract representation of these images in the latent space. Now, if this whole thing is trained good enough, then if you take the trained latents of all those images, they contain very rich information in a very low-dimensional way. These informations are usually abstract, but we can, if you want some intuition, it might contain, say, the type of object in the image and the pose and or the overall color or something. They're abstract, but if you use these latents to do classification or other type of things, it works very well. So this type of things where you learn good representations of data without supervision is called representation learning. So the question is, can we take, for example, the autoencoder into our framework where we instead operate on the event files and light curves? And it turns out it's not direct because, first of all, our input, which are the event files, it has very different length. In images, all images are of the same size and resolution, but in our case, the event files have very different photon counts. So the input is variable length, but someone might ask, we can obviously use RNN for recurrent neural network for input of different length, right? But it turns out that if we use RNN for input, it has a lot of difficulty in fitting because the thing is that the RNN is usually used on time series, where the time series contains very high signal-to-noise ratio. In our case, although the input is still technically a time series, it is just the time points, which can be very noisy due to the Poisson nature. And in fact, the RNN doesn't fit very well. Also, another reason is that our input is the event file, and our output is the reconstructed light curve, which are different type of things, instead of the same thing in the case of images. So what I'm saying here is that naively transitioning autoencoder into our situation is not straightforward. So what I'm going to propose instead is called an AutoDecoder, which is less heard than autoencoder, but it's already been popularized in machine learning literature in recent years. So for those of you who are seeing this in the first time, I'm going to talk about it step by step. So basically, an autodecoder just throw away the whole encoder part of the autoencoder and only consider the decoder part. But how do we learn these latents, right? These latents are instead just directly initialized. They're randomly initialized first, but then they are trained via backpropagating the gradient also to these latents. So at training time, the loss function produces gradient which are backpropagated to both this set of latents and this neural network.
Is it supervised or?
It is unsupervised. So the output is matched via the loss function that I defined earlier. They are unsupervised because we don't have any labels, but they're still gradient propagated by computing these laws. And these laws are just, remember, the likelihood plus the total variation loss.
Sorry, the latents, you need to have assumptions about them. So I think that maybe it's not here, sorry. So maybe it's not supervised and super unsupervised, I mean, compared to autoencoder, right?
Yeah.
So, okay, so can you put them in between? Because you definitely, I mean, you have open, right? So it's just, you start from latent to output, it's not from in to in, right? So, am I clear?
Right, so I mean, the assumptions you put for, it's very weak, I would say. I just put a Gaussian prior or equivalently an L2 regularization on these latents, but not any fancy domain knowledge. These latents are actually updated later via gradient descent.
Sorry, question on, do you have any prior on the distribution of the latents? Like if you wanted to use this as a generative model like in a VAE, you want to have some regularization, right, in the
Yeah.
license space?
Exactly. That's the VAE. Here I'm using an AutoDecoder, so it's not actually a variational because we are not looking to generate any event file or something. We're trying to learn the representation.
But it still feels a bit weird to not have a continuous representation, right?
Yeah, exactly. So that's why I'm putting an L2 prior, an L2 penalty only latents. I'm going to introduce pretty soon. But yeah, this choice is like more flexible because you just need to ensure a compact manifold of latent. Yeah, more details on that later. So here I'm first trying to like introduce like the generic AutoDecoder. The last point is that, remember, for the autoencoder, if we want to produce the latents, we can just pass the data through the encoder to produce a latent. But for AutoDecoder at test time, what we need to do instead is do test time, what they call test time optimization, meaning that we freeze the weight of this decoder. And for a new data point, we initialize a new latent, and we only fit that latent for a certain amount of iteration for the at test time or at inference time. So this is one of the major drawbacks of AutoDecoder actually, is that it takes more time at test time to produce a new latent. So we need to do iterative optimization. But compared to the drawbacks of autoencoder, in our case, this is, I would say, a reasonable price to pay. So, specifically in our case, this is the whole pipeline visualization of the PPAD, which is Poisson Process AutoDecoder. So, all of this is probably a review. So T is any time that we're interested in. So we first do a positional encoding, which is the sine, cosine encodings to produce a vector called gamma T. So we concatenate this vector with a randomly initialized latent for each event file. We pass this through a ResNet decoder, and it outputs a single value, which is the light curve value at that time t. That's for a single time. Now we can sample very densely at any resolution, let's say at like 10,000 time step. Then these time step forms a light curve, and we can compute the loss between this light curve and our input event file via the loss I defined earlier. And this loss backpropagate the latent through both the ResNet and, backpropagate the gradient through both the ResNet and the latent. And that's the full pipeline. Hope everyone's not lost right now.
Sorry, before you go. So when you are training, so you're going to backpropagate through the weights of the ResNet, but also the values of the latent spaces, right?
Yeah.
So at training, you're updating the weights and also the latent values for a single example or for a whole bunch of examples.
Right. So the ResNet is shared. So all the data points use the same ResNet, but we have a different latent for different data point. By data point, I mean event file. So each event file has its own latent, which contains information on the type of patterns of this event file. And that provides enough information for the ResNet to reconstruct the whole light curve. Hope that's clear. Another iteration on the loss function, we now have 3 terms of loss function. First term is the negative log likelihood derived from the Poisson process. Second term is the total variation penalty that we want to enforce on because we want the reconstructed light curve to be smooth enough. third term is another regularization term on latents because we want the latents to be in a compact manifold to prevent the latent from going to infinity, which prevents the training from converging. Now, if we add them, the training converges very well.
So what is Z?
Z is the latent. It's the number it's the letter that I use for latent. Yeah, so we're putting a L2 penalty, which is equivalent to a Gaussian prior, only latent.
And what determines the number of n? I'm just trying to generalize this pattern in my head for any given problem, right? So how do you know what is the little n, right? That's actually the values of that, and or even capital N. The truncation in your series, what determines that?
Yeah, so this n is just the number of events in an event file. So the total variation, I have two set of points. This set of points is all the arrival times. So this little n is just the arrival time, the photon counts. And this n can actually be anything. So because you basically need a grid of points to calculate the total variation penalty. It depends on the level of resolution you want. I'm using 4096 in my case, but it's kind of an arbitrary choice.
Sorry, but this is kind of not amortized, right? Sorry. So if you have a new observation and you want to test how good your reconstruction is, you have to first fine-tune the latents and then show the reconstruction?
Yeah, exactly. If those event files are in my training set, then I don't need to fine-tune. But if it's a new data point, a new event file, I need to fine-tune. It's actually what I want to reiterate in this slide. So at training, right, we have big M number of event files. So I prepare also M number of latent and this neural network weight, and they are optimized together during training. At test time, say if we're given a new data point, then I initialize a new latent Z, and I freeze the neural network weight, and I only optimize that latent.
Right, but what was the advantage versus having an autoencoded way is amortized, right?
It's definitely, I mean, if you only consider this, the autoencoder is better. But like I said, the autoencoder is having a really hard time fitting these noisy event files. So it will be actually really good if someone can get the autoencoder working in future work. Yeah.
Hi, good talk so far. I guess I have more of a practical question. So how long does it take to retrain for each new event? And how long is it between new events on average? So can it keep up with real-time stream of X-ray detections?
Yes, definitely. The event file I'm using is 8 hours, and it takes, let's say, 10 seconds to, trim. I mean, although for autoencoder it probably takes milliseconds, but like, I think 10 seconds is still fast enough in practice.
It will probably take longer to actually detect the sources in a new Chandra observation than actually doing this, because this architecture first needs to isolate the event files that correspond to a particular source in the field. So you need to first detect the source and then get it. So, but yeah, it's a good question, because one of the things people have been asking about is, can Chandra have, or X-ray telescopes can, an alert system that could find new transients and things like that? Good point.
Right, yeah, so now it's time to show some experiment results. I'm gonna introduce a very light pre-processing. So I'm taking 100,000-ish event files from the Chandra Source Catalog. I truncate them into 8 hours because we want an apple-to-apple comparison. And recall that earlier I've just ignored the energy bins. Now I'm gonna add them back. So I'm putting the energy into 3 bins, soft, medium, hard. Notice that this can also be generalized because we can just let the neural network output a two-dimensional field, which one-dimensional on the image, another dimension on time. But as a starting point, I'm just bend the energy into three. So the neural network now output three values, one value for each energy band. These are all the pre-processing I'm doing, so pretty much relevant file. And first set of experiment result I'm showing is the Yanke reconstruction. So these are actually the four event files that I showed at the very beginning of my talk. On the top line is, on the top row is the total counts. And this is it counts for the low, medium, and hard energy bands. And we can see that the reconstruction result, I would say, is pretty good because this flare and this dip periodic variations are all captured. And for this low count, possibly homogeneous event, instead of fitting to these artifacts, it's actually reconstructing a pretty flat line curve. Although it still has some, I would say, room for improvement. For example, this one, it's kind of fitting the artifact.
It says battery should run in low. Do you have it plugged?
So let me ask them a question on the what is this polyimaging and no reference?
What is one?
Like the cap here.
Oh, right. Yeah, these are different energy bands. So, like soft, medium, and hard.
Oh,
I should correct my labels. They should be soft, medium, and hard. And this whole thing is it has a kind of hierarchical nature because, say, this one looks pretty similar, but notice that this one is fitting a flat line curve, where this one is fitting something different. This is because this whole event file is using one shared latent. So that latent contains information for the properties of that source in general. So if it sees that the soft and medium band has these variations, it'll also have some similar variations in the hard band. So that's why you see kind of similar event file, but different reconstructed line curve for different events. Also, this one, they're pretty similar, but the reconstructed one is very different.
One question again on the decoder versus autoencoder. I guess one issue is that you're more prone to overfitting, right? So that's why you need to do all these regularizations because you're doing inference per object, right? Whereas the autoencoder has some implicit regularization on you have the same encoder for all the line curves.
I'm using the same decoder here, so.
Right, but you're fine-tuning the latents per observation, so I could see how that would lead to more overfitting, right? So you need to do more regularization than you would otherwise.
Actually, if you try the autoencoder, it overfits a lot, and it's just complete trash. This problem has a very, very different nature than other problem where autoencoder works well.
I think a good discussion to have later is how a good architecture of that autoencoder could be that captures the same amount of information. I think I see Carol's point, but I also know you tried an autoencoder and didn't get very good results. So
I can talk about that later towards the very end. So this is Yanke reconstruction results, and remember that I also said this thing can learn a good representation at the same time. So here I'm showing the visualization of latent space. The latent dimension I'm using is just 8, so it's an eight-dimensional latent, and now I'm projecting it onto 2-dimension by using PCA and Tisney, respectively. Here you're seeing PCA colored with hardness ratios 3 hardness ratios. So very obvious pattern here. And here we're visualizing intensity versus colored by variability probability. These variability probability are computed from the regular radio algorithm, which kind of indicates how variable a source is. So if the numbers are higher, it means it's more likely that a source is variable than homogeneous. So you can see that these brighter colors are all relatively clustered together. So all these type of plots demonstrate qualitatively that the latents have very rich information about the property of sources. These are qualitative results. Then I also did some quantitative experiments. So what I'm doing is I'm taking these trained latents, 8-dimensional. I'm fitting very simple machine learning models using extra labels, because now we're interested in downstream tasks. So I give them some other labels and train a very simple random forest with 100 trees and default hyperparameters. I didn't spend any effort tuning them. I'm doing a 80%, 20% training test split without any validation set. So no cross-validation. Here I'm trying to predict the hardness ratio. Here I'm trying to predict whether a source is variable. Here I'm trying to predict the actual source type, where I used some human verified labels from previous work. This is a 7-class classification. And here it's a simpler 2-class classification. Yeah, and you can see these results are pretty good, especially considering I'm only using very naive regression classification random forest. Specifically, these numbers can match some of the previous work where they use hand-designed features. I would say that with better tuning of both this whole pipeline and this downstream task predictor, you can probably get even better results. But I should say tuning the prediction head is not the focus of this work, because I'm trying to show that with a good representation, you can get decent results with very simple downstream patterns. Another use case is anomaly detection, right? So here I'm taking this top left event file and showing the reconstruct light curve. I'm using this as a target and finding 7 other events where it's closest neighbor in the latent space. So you can see that some other events also have this flare-like behavior, such as this one, this one, this one, this one. So it has the potential of anomaly detection where we have some specific pattern in mind, and we just need to find the nearest neighbors in the latent space to discover similar event files. Yeah, that's actually all the results I want to show. And final slide for some future work. First of all, this whole thing can obviously be scaled up. It can be scaled up and tuned better. And also, if the whole thing is tuned good enough, we can actually do some downstream tasks. So the experiment I'm showing, I'm all using human verified labels. But there's actually a million more unlabeled sources, and this can hopefully be served as a good labeler, or like for some reference labeler if human need to fine-tune them. And finally, which is I think a more interesting research question, is if we can bring back the autodecoders for better learning. If you want to hear some more details, like a very, very hard thing for autodecoder to work is that our input time event files has very different scale. For example, if you consider like a usual time series where they use Rn or something, the time series values are all pretty uniform, say, let's say between 0 and 10 or whatever. The time series values are all within some good scale. However, if we think about our case, say our case are just the arrival times of photons. It can range from 0 to 8 hours. Now we can obviously scale them and to let them scale from 0 to 1. But if the whole thing is scaled from 0 to 1, then between two events, the time difference might just be some milliseconds or 10 to the negative 6 seconds. And it has very, very small numerical difference in terms of the neural network to learn. Because, this special nature of our case is just an increasing series of time where if you think about the first and the last, it's a very large scale. But if you think of the first and the second, it might have some very small scale. So it's very hard for an RN type or like LSTM, whatever type of encoder to differentiate those kind of patterns. So it's a very good research question on how to introduce the LLM encoders back to this pipeline.
Thank you.
Yeah, that's actually all my talk.
Thank you. A couple questions?
Yeah, great talk. So I had a question about one thing that I noticed, or one thing that I expected to see from the latent space, is that all events with very low variability that were essentially homogeneous with Poisson noise would map to the same point in the latent space. And I think one reason why it's not is because I didn't see any normalization of the light curves in along the vertical axis, which you see with a lot of continuous light curves before you train a decoder or an autoencoder. And I know it's harder here because you're dealing with absolute counts versus dealing with a continuous light curve. So I guess my question was, have you considered ways to normalize the counts in some way such that you could maybe reduce the dimensionality of your latent space and better isolate the variability itself?
Yeah, definitely. So first of all, I'm not sure whether I should, because there's a low count homogeneous event and a high count one could still be different, right? But if we want to normalize it, we can obviously do that in the loss function. So basically, I just want to modify this likelihood where I do some normalization in terms of total events.
I think it's an interesting point that you're making about expecting all the ones that are constant to map to the same point. Would that also, I mean, what about energy differences? Because the input also includes energies for the photons. So would you still expect them to map to the same point if they are constant, but if the energies of the photons are different?
I think it depends how you encode it. Right now, they would map to different points, but if you normalize it, they would map to a similar point in the latent space.
Yeah.
I think whether you do or not would depend on what you're trying to get out of that latent space. Like for example, a lot of the downstream tasks here seem to be classification based on the shape of the light curve or the variability. In that case, you wouldn't care about the energy as much as kind of energy is changing.
Yeah, I think one interesting downstream task is actually to find transient light behaviors where the light curve depends on the energy, actually. So where you have a light curve in the high energy photons that looks different from the same source in low energy photons. So anyway, it's an interesting point to this. Yeah, thank you.
Definitely a good future direction.
Sorry, Razi, you had another question or point to make?
Yeah, actually, sorry. That's like more of the clarification. The second point of your future work, downstream the task, I didn't get what do you mean by that. Like,
Right. So right now, all these downstream tasks I'm doing is with humanly verified labels, just to test my thing works, right? But like, what astronomers or researchers actually curious is like trying to find new sources, or like try to label previously unlabeled sources. Those things that can actually like be helpful, I haven't done. Because that I don't have a way to verify whether my predicted labels is true or is accurate.
Oh, I see. So you want to compare your predictions with the other observations of similar type? Is this what you're trying to say, or?
Like, think about like when a machine learning model is in verification phase versus actual production phase. This point basically means to put this into production. That's the future work. Yeah.
Thanks, yes then.
Yeah, thank you. Seemingly, the fact that the time measurements are quantized didn't have any effect on this analysis. Is there some theoretical or empirical way that you could verify that?
What do you mean by time measurements are quantized?
Do you picture that the time can be any irrational number, the time measurement?
It's already, I'm already using any irrational number.
So you can predict.
The times, for example, are integers times 3.2 seconds in a typical ASIS.
No, it's actually any time. It can be any time in my case. So, for example, here, right, are the arrival times. It's just can be any irrational number.
But in the data, it can't be.
We have not incorporated the readout times or ASIS.
Presumably, that isn't important from the results you presented. So what I was asking is if there's some a priori test that you could or would or apply. It seems like you should apply some criteria.
So I guess what you're saying is, regardless of what the readout time of the detector is, the underlying physical phenomena that shows this should be there, and therefore the result should not depend on the readout time.
In particular, if you took 100,000 ASIS observations, there's probably 5 different quantization scales.
Oh, I didn't know that. I didn't know there's like a quantization for the data. Right? So it's even before this happened. It's the data from. Right?
Yeah.
Yeah.
Sorry, we haven't thought about that aspect of the quantization. I think the fact, one of the main problems we were trying to solve here was the fact that any representation learning that has been tried on event files before relied on a sort of fixed size of the input. We're also trying to find a representation that could effectively find dips and flares, so transient phenomena. And so that has been the focus so far. But I think it's a fair point that there are some instrumental effects that in theory should not have an impact on the results, and they seem to not be having it for the purposes of this research, but it'd be good to think about those as well. Thanks, Dan. All right, well, thanks to the ones still standing. Good job. Thank you so much, Yanke. Thank you again.
Okay.
And if people have